the harmonic series is a very important series, and it's going to be an excellent source of examples in many situations. And as you will see, it will pop up many times throughout this playlist. So what is the harmonic series? Well, the harmonic series is the sum from n equals 1 to infinity of 1 over n. So it's 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 and so on. And here I have the graph of the terms of this series that go to 0 quite fast. As you can see, the blue dots. And the pink dots here gives us the partial sums, the value of the partial sums. And here we are doing the first 100 terms. So you can see, well, you might think that maybe they will converge to something probably around 5 or between 5 and 6. Something like that, right? It looks like that's what should be. Now, do you agree? Well, let's see if we were right. Let's try to take a look at the partial sums, take the limit of the partial sums, and see what we get. Because remember, we only have the definition at our disposal so far. So here is, the first 16 terms of my harmonic series, and we're going to notice the following. 1 is greater than or equal to half. Good, you believe me. 1/2 is equal to 1/2, so in particular is greater than or equal to 1/2. The next term is not greater than or equal to 1/2, but if I add the next 2 terms, then their sum is, because you see 1 over 3 is bigger than 1 over 4, and 1 over 4 plus 1 over 4 is just 1/2. And the next term, again, obviously is not bigger than 1/2, but if I add the next 4 terms, we have that their sum is bigger than 1/2, because each one of these terms is greater than or equal to 1 over 8, and we have 4 of them. So 4 times 1 over 8 is 1/2. And then we're going to look at the next 8 terms, and we're going to have 8 terms. Each one of them is greater than or equal to 1 over 16. So we end up with, again, their sum is greater than or equal to 12. Indeed, it's strictly greater than. And why are we doing this? Well, this is going to help us find at least some of the partial sums. For example, S2 is 1 plus 1/2, so this is bigger than 1/2 plus 1/2, which is 2 times 1/2. And now, you see, I'm not going to worry about S3. I don't know, but if you see from my picture, the next one I could look at is S4. S4 is 1 plus 1/2 plus 1 over 3 plus 1 over 4. The way I bounded it, what I'm seeing is that this is bigger than 1/2 plus 1/2 plus 1 over 4 plus 1 over 4. But these two 1 over 4s combined give me 1 over 2. So then I have 3 times 1 over 2. Okay, now the next term here, it seems that we can easily control, is the 8th one. So we're going to look at the 8th partial sum, right? S8, we looked at the first 8 terms of my series, and then we're going to do the same trick, and we're going to bound it. We have those last 4 in this partial sum. Each term is bounded by 1 over 8, and there's 4 of them, so we end up with 1/2. So here we have 4 bits that contribute 1/2 each. So I have that this is 4 times 1/2. Then I will continue doing this process, and then S to 2k. I can write it like this. Well, I'm going to group the last, in this case, the last 2k minus 1 bits. And I'm doing this grouping, right? First I grouped 2, and then it's well, the first 2 plus the next 2, and then the next 4, and then the next 8, and then will be the next 16, and the next 32. That's how I'm grouping them. So what we're going to end up with is the following. Well, we have part 1, again, greater than or equal to 1/2. 1/2 greater than or equal to 1 over 2. This one, we said that the sum of 1 over 3 and 1 over 4 will make the 1/2 contribution. Then the sum of the next 4 terms will give us another 1/2 contribution. Then this last bit here, we have 2 to the k minus 1 terms, and each one is less than or equal to 1 over 2 to the k. So in total, they contribute again 1/2. So we have k minus 1 bits, and each bit contributes 1/2. So we have that s2k, 2 to the k, is equal to k plus 1 over 2. Therefore, for any n, s2 to the n is greater than or equal to n plus 1 over 2. Oh, pretty cool. Because what happens if I take now, well, the limit as n goes to infinity is going to be infinity, right? Because by the Archimedean property, I know that the sequence of the s2 to the k is not bounded above. And if a subsequence is not bounded above, then my whole sequence cannot be bounded above, right? So if my sequence of partial sums is not bounded above, and I know that my sequence is increasing, then that means that my series is divergent, and it diverges to positive infinity. So at first it looked from the graph that actually the sum should kind of stay like less than 6, but it escaped to infinity. And this shows how big, in a way, infinity is. We're adding up very small quantities that actually become smaller and smaller every time. But at the end, we are adding infinitely many of them, and they ended up adding up to infinity. Then we had something like 1 over 2 to the n that had a finite sum. We'll see, but maybe some others, they kind of decrease a lot faster, and that will give us more control. But in this case, we have a case of terms that are very small, that they become smaller and smaller each time. And yet, because we're adding so many of them, we ended up escaping to infinity, just very, very, very slowly.